The RY gate is generated by the Pauli Y matrix. In a quantum circuit, the RY gate is often represented by a box with the letter RY inside it, followed by the parameter theta in parentheses. The wire representing the qubit to which the gate is applied is connected to the box. This symbol helps to visually communicate the operation being performed on the qubit. To perform a rotation around the y-axis using the RY gate in a quantum circuit, you simply apply the gate to the qubit with a specific angle theta as the parameter. This will rotate the state of the qubit by theta radians around the y-axis. This can be useful for creating superposition states or for manipulating the phase of qubits. The RY gate is a quantum gate used to rotate the state of a qubit around the y-axis by a certain angle, denoted by theta. When the RY gate is applied to the computational basis state ket0, the resulting state is a linear combination of ket0 and ket1 with a phase determined by theta. Specifically, the state after the RY gate is applied is cosine of theta over 2 times ket0 plus sine of theta over 2 times ket1. On the other hand, when the RY gate is applied to the computational basis state ket1, the resulting state is also a linear combination of ket0 and ket1 with a different phase determined by theta. Specifically, the state after the RY gate is applied is cosine of theta over 2 times ket1 minus sine of theta over 2 times ket0. So, the RY gate acts differently on the computational basis states ket0 and ket1, producing different linear combinations of these states with different phases. This can be useful for manipulating the state of a qubit and creating superposition states with different amplitudes and phases. The RY gate is a fundamental quantum gate used in quantum computing and quantum simulation, which rotates the state of a single qubit around the y-axis of the Bloch sphere by a specified angle. The matrix form of the RY gate is a 2 by 2 unitary matrix with elements cosine of theta over 2 and sine of theta over 2 in the diagonal and opposite off-diagonal positions, respectively. When we raise the matrix form corresponding to the RY gate to the nth power, we obtain a matrix whose elements are scaled by the cosine and sine of the rotation angle raised to the nth power. This property makes it useful for simulating the time evolution of quantum systems efficiently, as well as for designing quantum algorithms for various tasks. For example, the nth power of the matrix form corresponding to the RY gate can be used in quantum phase estimation algorithms, which are used to determine the phase of a quantum state with high precision. It can also be used in quantum search algorithms, such as Grover's algorithm, which are used to search unstructured databases with a quadratic speedup over classical algorithms. When the RY gate is applied multiple times to a quantum state with real coefficients, the resulting state undergoes a sequence of rotations around the y-axis of the Bloch sphere by angles that are proportional to the rotation angle of the gate. Specifically, each application of the gate corresponds to a counterclockwise rotation of the state by an angle of theta over 2. As a result, the state vector traces out a path on the surface of the Bloch sphere, which can be visualized as a spiral staircase-like shape, with each step representing the rotation caused by the gate. Moreover, the direction and shape of the path depend on the initial state and the number of gate applications. This geometric property of the RY gate is useful in quantum algorithms and quantum simulation, as it allows for efficient manipulation and analysis of the quantum states. For example, the path traced out by the state vector can be used to estimate the eigenvalues and eigenvectors of a Hamiltonian or to perform quantum phase estimation.